Okay, so we have the second lesson here, and this is the entire lesson that we have in this section. Okay, so it's 1, 1, 1, 1, 2, and then after this it's going to be 1, 2, 1. So this is the last lesson. There's only 2 lessons in this section. This is basically just wrapping up what we were talking about as far as exponents, simplifying and solving when exponents are involved. The key for this is when we solve an equation, we always use the opposite operation to get rid of whatever's connected to x. We're trying to isolate x. We want x is equal to all the other stuff. We want to isolate onto the other side so that x is by itself. So I'm actually going to start with this side because it's more related to what we have been working on yesterday. So just to look at it, if I had a problem like this and it was 2x is equal to 10, what operation is going on there? Multiplication. And what would we do in order to isolate x? I want to get rid of the 2. I would do so by dividing. You guys totally catch it. That's what I wanted to hear, that we end up with 5 because we do the opposite operation on both sides. As long as you do it both sides, you can do a lot. Okay. It has to be to both sides. You have to use the opposite operation. So let's look at this. X squared is equal to 25. What operation is going on here? Think of PEMDAS. Which one of those is happening? The exponent. Okay. Now the exponent, it's to the second power, right? So what is the opposite of squaring something? What's the other direction? Square root. You guys got it? So think of it this way. So the big circle. If I have 5 squared, what do I get? 25. If I take the square root of 25, what do I get? I get back up to 5. It's just a big circle because they're inverse operations. So I'm going to go ahead and take the square root of x squared. I'm going to take the square root of 25 and solve that out for me. Cancel it out. You can cancel out this 2 and 2 because the square value and the square rooted value are inverses. That's going to isolate now x. Now I put this here just to be able to cancel out the 2's, but are we gonna get confused when we just see the square root by itself? No, because it's the first root you can take. Okay. If I had a situation, well, we'll get to that situation. Let's hold back. Now, in Math 1, you may have just been taught that the square root of 25 is 5. What's the other option, though? There we go. Plus or minus 5. Think about it. Square root is asking what times what gives you 25? Negative 5 times negative 5 also gives you 25. Just want to bring that in here. The plus or minus is going to come in at the end of the unit when we get to complex numbers. Okay. Imaginary numbers and real. Okay. Everyone feeling okay with this? Inverse operation. It's going to be quick, right? You guys have seen this process a little bit already. When we get down to here, there may be some that need a little bit more support. That was an equal sign. It was kind of messy. Under rational exponent. All right, let's see what happens when we have a root. And exponents and roots are those inverse operations. So here we have the cubic root of x. I want to get rid of that cubic root. I want it, the next step, or whenever I get there, to be x is equal to something. I want to solve. What should I do in order to get rid of the cubic root? What do you think? Anyone have input on that? Yes. Cube both sides. Just as the square was, the x squared was isolated down to x by square rooting a squared value. If you have a cubed root value, you can cube it and cube both sides in order to isolate. So it's the third root of x. If we cube it, it isolates the x by itself. And 2 to the third power is 8. What if I had the 71st root of y is equal to 10? How do I isolate y? raise both sides to the 71st power. It's a horrible root to have to do, but I want you just to see those always isolate, right? If I had y to the 71st, what am I going to do to isolate the y? 71st root, 71st root. Okay. Those are always going to cancel. Just keep that in mind. I think that's reinforcing enough, right? Yeah. Rational exponents. X is now raised to the 2/3. It's equal to 25. We want to actually keep it in exponential form like this. We're not needing to convert it. We just need to isolate x by itself. And I want you to talk to your neighbor, or think about it first, and then talk for about 30 seconds. And let me know what's a strategy we can use. Think of your power of a power property. Think about your exponent properties. Maybe look on those notes. That's the hint if you want to discuss something. So let's try that. Yeah, probably everyone needs to look at those exponent properties and then talk to someone, see if you go to sleep. You guys have an idea in the back? Not yet. Okay. Let's see. I'll let you play with this. If I can get rid of the 2/3 exponent, the next line would have x to what power? I want to solve for x, and if I solve for x, it's x to what power? X to the first power, right? So how do we go from x to the 2/3, essentially, to just have an exponent of 1? Think of the power of power property. You got it now? Yeah, you got it. If you're not sure on this, maybe you didn't learn it. Once you see it, you get it. All right, 10 more seconds. What's that shirt? What's that shirt, Tom? Like old school? No, old school. There's somebody new named D'Angelo. Who has an idea on this? Maybe from talking to each other or looking at your properties. What can we do in order to isolate x in this case? What should we do? We're going to raise it to some exponent. Take it. Convert forms. Convert. Let's not convert forms with this. Once you see this process, you're going to have to convert form to get an actual tangible answer in the next step anyway. But here, let's just isolate x. In fact, you won't have to solve for an actual value. I think it just says to simplify it, solving for x, and then leave that without evaluating further. What do we think? Yeah, Sean.
3 over 2.
There we go. 3 over 2. 3 over 2. What is, those that are good with shortcuts, what is the power of a power? What am I going to do with these two exponents in order to evaluate just this process right here? What will I do? What do we do when we have two exponents, an exponent to an exponent, power to a power? What do we do with those two values? You multiply. If I multiply 2/3 and 3/2, I get 6 over 6, I get 1. That's how I'm getting rid of that exponent. And it's not the negative reciprocal, it's just the reciprocal of the fraction here on both sides. And now that's going to be 6 over 6, so those are gone. See? 2/3 times 3/2, 6 over 6. So we got that x to the first, no need to have it there. And then we have that 25 3/2, right? Yeah, I mean, you could have. Now, you wouldn't want to convert it first. They're going to allow you to leave the answer like this for the classwork. But now, if we needed to find an actual tangible an actual value, then we would have the square root of 25, and we'd be. We would also have to cube it. That's where the power would go. Okay. But I don't need you to convert it to solve it. I think for the classwork, yeah, you can leave it like this. Okay. All right. Thumbs up, sideways, down for what we've done so far. Pretty good. You seeing how we're connecting things? Perfect. Last one. These, remember, were related. These are going to be related too. So what should I do to both sides to start? Actually, this one has a slightly different path. It's the square root. For those that really like the 2 plus part of this, think of it this way as well. We have, with this x to the, that's not quite. Yeah, you can think of it this way. It's like that as well. That's one way to solve it, straight off. You can erase that. If you want to try to play with that, you can. But we can also just do it with 2 steps. Bless you. What's our first step? I don't like that square root symbol. Let's get rid of it by, say again. Let's square it because the square root and the square are going to cancel out. And then we have x to the 3rd power is equal to 25. You know, I like this process. I like this better. I mean, it's just 2 quick steps. You see the path a little clearer. Logically, I think it's a little easier to see. Maybe not for you. What am I going to do now to get rid of this cubed exponent here? X cubed. We want x, not x cubed. Right? We're so used to saying square root. But there's all those kind of roots. Now we got x is equal to. The cube root of 25. When we take this, are we going to have to do plus or minus? Are we going to have to do plus or minus? What do you think? Let's say that we had, the cube root of 8. What is the cube root of 8? What times what times what gives you 8? 2. 2. All right, so this equals 2. If I had negative 2 and I put it in there, negative 2 times negative 2 is 4 times negative 2 is negative 8. So you're going to see when you have the roots that are odd, right? When you have the roots that are odd, you don't have to put plus or minus. It's just going to be the positive value of that. Okay. You see what I'm saying? So the 2nd power, 4th power, all the quadratic roots. All right, so we are going to keep it like so because the classwork allows us to do so like that. Otherwise, that you probably could just evaluate on your calculator. Evaluate. All right, so far so good. Simplifying exponents, thumbs up, sideways, down. Good to go. All right, I'll see here. All right, this is mostly just abstract work. This is abstract. It just is helping us define our different system of numbers here. Because, there are different types of numbers. They include other, subsets of types of numbers. Now, I'm not going to go over the whole system, but we do need to get used to irrational and rational numbers. So these are critical for numbers 4 through 6 in the workbook and the book. But I want you to give me some details. What do you think? What do you know about irrational numbers, like pi, like root 2? What are some qualities that these irrational numbers have, defined by the script p here? Yeah, it's Ethan. Ethan, what do you think? Okay, can I say non-terminating?
Yeah.
Non-terminating? Yeah. Overrated. It's like terminating. All right, what's another quality? Who else has a quality of irrational numbers? It never ends. Is it easy to remember all the digits of pi because, you just remember 10 and then it repeats? What's the other quality of our irrationals? Non-repeating. Right? Non-repeating. That's good. There's a couple others we throw in there. E, right? Which is having to do with our natural logs, 2.71, blah, blah, blah. What's another one? Anybody know another irrational? What's that one? I don't have them all memorized, so if you know them. We're good with 3? 3 examples. I like to remember this because it's irrational is the capital P, P for pi. Just keep it that in mind. Okay, rational numbers we know a lot about. It has a Q because I think of it as like a quotient. Quotient is the answer to a division problem. Quotient, rational number, it's fraction, right? So quotient is like a fraction ratio. 1/2, 3/4. Examples could go forever. We know these. Okay. So this is what happens when you combine them in different ways. And the way I think about it is, if you combine rational numbers, you always end up with a rational number. If you're adding it, multiplying it. Okay. But anytime you have a combination of a rational and irrational, you always end up with an irrational number. Now, that is a pretty straightforward way to remember it. This is helpful just to know if you have a simple problem like this, where should you end up with? What value should you end up with? Honestly, this would be super helpful just to have this photographic memory in your mind. So you get to the SAT and it's talking about 2 values. If you can conclude before you start that it has to end up being an irrational number, and the only irrational number of your 4 selected is pi, guess which one I'm going to pick? Pick the irrational, right? So this is like a shortcut, again, almost reinforcing like a meta idea of how to know if you're on the right track. So let's see if it makes sense. Root 2 is irrational. And 3 is rational, 3/1. So thinking about that, who has a calculator out? Anybody have a calculator out? If you have a calculator, pull it out. Let's go and do root 2 and see what we get with that value. All right, I'm getting used to using a calculator again. This is one that I found in the desk. So still learning how to use this. Casio's always a little tricky. I always had TIs when I was growing up. Tricky. All right, root 2 is, and this doesn't give me the decimal. Okay, 1.4142135562, and it is irrational, so those are going to continue and not repeat. Okay, so just imagine that. You have, in essence, I kind of think of this as, root 2 is 1.41, and it's like a long tail. The tail goes on forever, never repeats. But if I'm simply adding 3 to that, right, I'm going to end up with 4 and the same tail trailing forever. You see how we're just adding to the whole number, really? It's going to keep it that way. Okay. These are things, that's almost like, well, what's the trick to that? There's no trick. It's a real basic idea. It's just a different way to conceptualize 2 different types of numbers, which is helpful for our next complex number journey here we're doing. How about this? Pi? Who knows a good decent number of pi? It's actually something I've never endeavored to do very far. Does anybody memorize the first 10, something like that? First 5, first. How about the first 3?
3.14.
Okay.
And I'm just going to put the tail. How about that?
Yeah.
So if we have 3.14 long tail, and then we just add 1 to it, what are we going to end up with? Oh, we multiply. I changed this to multiply. If we multiply, we get the same thing. How about if we add it? Is that going to make a difference?
Plus 1, so it'd be 4.
Right, so we're still going to end up with an irrational number if we multiply it or add it, because we know that this right here, this is our rational, and this is our irrational. So you just kind of have to remember that breakdown. If they're different, you always end up with the rational. How about here? Root 25 is 5, so we definitely know we have a rational number there. Times root 2, which 1.41 with the tail. So what are we going to essentially end up with is it's going to end up with that irrational number because they're different. You're combining the 2. Is that is that landing? Thumbs up, sideways, down for that. This one's all abstract. This side of the board's all abstract. Okay. All right. That's good. That's good. What else do we have? Nothing. Okay. That's good. All right. So I saw that maybe 4 people signed up, subscribed to my channel. And remember that this is my only sense of self-esteem and worth in the world. So I need y'all to subscribe And I wanted to know if you thought, is there a good giveaway that I can give? Maybe for the 200th subscriber. I actually asked the last class. But if you have better ideas, I'll change it. Does anyone have, what should I give out? Some kind of candy? Yeah, that's good. It's cheaper. Good choice. Last year, someone's like, Amazon gift card. They don't make $5 Amazon gift cards, do they? No. All right, so rough limit is like $3 or $4 for candy. What's the best kind of candy for $3 or $4? What do you think? Oh, big Costco box of.
Yeah. You have it like year round.
It's true. I don't have a Costco membership though. All right, I'm gonna suggest it again. Most people like king size Kit Kats, right? The big Kit Kats, right? No, not this group. King size Reese's. You guys not? But we can't eat it in here. But I can give it to you. All right. I think I'll think on it.
Yeah.
All right. I just broke my own rule. I made this whole spiel about no peanuts, and I suggest that. Okay, so it's probably going to be Kit Kats. This is really important, guys. I want you to give some thought to this. Just kidding. All right. Let's entice people. The 200th. Parents, you can't win. You can't win. The 200th will get a king-size Kit Kat. So let's do Kit Kat on 3. 1, 2, 3.
Kit Kat.
How about subscribe on 3? 1, 2, 3.
Subscribe.
Okay. How about no peanuts allowed in class? 1, 2, 3.
No peanuts allowed in class.
We're health conscious too. Look at that.